Our first speaker this afternoon is George Taylor, Oregon State climatologist, faculty member, Oregon State University College of Oceanic and Atmospheric Scientists. He manages the Oregon Climate Service, State Repository of Weather and Climate Information, and has a staff of his own, which I could do with. He is going to entertain us and educate us on teleconnections. So I hope I can follow it, because I don't even know what they are. Thank you very much.
Thank you, Richard. And it's a pleasure to be here today. A couple of things I want to point out that have changed. Some of you may be aware that I have recently announced my retirement, so I am soon to be the former state climatologist of Oregon. I'm retiring as of May 1st. And by the way, for the record, I am taking leave time from Oregon State today. I'm taking vacation time this week to be here. And I'll say, in addition, that what I say today are my own opinions. They do not represent those of Oregon State University, nor the state of Oregon, nor anybody with half an ounce of sense. So I want to talk a little bit about teleconnections, and you may know about teleconnections, but I'll also confess to having a left coast bias. I have spent my entire life west of the Rockies, mostly along the west coast, born and raised in Santa Barbara, educated in Utah, living for the last 19 years in Oregon. So I'm very much Pacific-centric in the way I look at things, and I happen to think that the Pacific Ocean dominates not only the Pacific Rim and areas around the rim, but in fact dominates world weather. I also want to ask about the lights. I think in times past they've dimmed the lights somewhat, haven't they? What do you think? Well, I don't know. If you can read that okay, we can just leave it the way it is. It'll keep you awake, yeah. That's the tough thing about talking right after lunch. I mean, a lot of people are out taking walks, so it's kind of a skeleton crew, and most of you are sleepy. So every now and then I'll do something like that to wake you up. How about that? Okay, teleconnections, what are they? For you, Richard, this is what they are. Weather that changes at one location that might be related to weather changes at other remote locations. Kind of a cause and effect thing geographically over often very significant distances. So the fundamental question really is what causes climate to change? And of course the answer is a whole lot of things, some of which we understand fairly well and a lot of which we don't understand very well at all. And I'm really going to focus primarily on the Pacific. But among the causes, is it human causes that cause climate to change, like greenhouse gases and land use change and smoke and dust and aerosols and stuff? Or is it natural causes like changes in sunlight in various forms, ocean conditions, volcanoes, and stuff? Maybe we should take a vote. How many of you think it's the first one? How many of you think it's the second one? See, I held my head up both times. How many of you really think it's a combination of the two? How many of you kind of have a sense of what it is, but you're not entirely sure? Hey, there's a lot of uncertainty in this field, let's face it. Once upon a time it was really simple. I do seasonal forecasts every year, and all I would really do 15 years ago is see, well, is it an El Nino or a La Nina? And then we started discovering new things, and now there's so many variables that we have stumbled upon or discovered or learned about that what I find is that the older I get, the less I understand. So either I'm getting stupider as I get older, or we are getting wiser and more mature, and I hope it's the second one. And of course I believe that climate change is because of a combination of human and natural causes, and I think like many of you, I believe that the one on the bottom has, at least up to this point, been the dominant one rather than one at the top. Now here are a couple of ways that we can determine what causes climate to change. We can construct a mathematical model that simulates the ocean, atmosphere, biosphere, cryosphere. That would be the sea, the land, the living things, and the ice. And I'm not opposed to modeling. I've done quite a bit of modeling myself, and that's really an acceptable thing to do. Or we can study variations of climate in the past and try to determine what caused them. And for the work that I do, I picked number 2. Partly it's because in my role as state climatologist, one of my tasks is to put current weather and climate into historical perspective. So frankly, I spend a lot more time looking backwards than I do looking forwards. And so when I study climate in the past, I try to determine cause and effect relationships and make inferences from that. Here's my hero. He was here a while ago, but he thought he was coming into Joe DeLeo's talk, and I said, no, this is my talk, and so he graciously excused himself. I promised him he could watch this on the videotape if there is one. Anyway, Bill Gray is, I'm one of his disciples. And the first time I heard him talk was in 1993 at the AMS conference on hydrometeorology in Anaheim. And Bill was just as excited as can be, and he could hardly contain himself because he said, you know, I think I found something here that maybe it's the unifying theory of climate. I don't know, but I want to tell you about it. So here's a picture that he showed. And this is based on some work by Wally Broecker back about that time, and it's a global thermohaline circulation, which according to Broecker operates kind of like a conveyor belt. And the idea here is that there is a net movement of warm water from the Pacific to the Atlantic and cold water back in the other direction some of the time. And in other cases, it either reverses itself or slows down. The point is that the Atlantic and the Pacific are out of phase with each other in terms of their temperatures. So when the conveyor belt, if it really exists, is really active, the Atlantic warms up and the Pacific cools off. And when it's less active or reverses, the opposite tends to be true. Now, because this is so big and operates on such tremendous timescales, it's really impossible to verify that it really happens. This is just a long-term net flux of temperature. But we can look at symptoms like Atlantic hurricanes and El Nino and La Nina events and so on and infer some things about it. So this is Bill's table. I think I'll walk over here. And what Bill showed was different time periods and some symptoms of the conveyor belt that would suggest one phase or the other. Atlantic hurricane activity would expect it to be enhanced when the Atlantic is warm. And during these periods, it was truly enhanced. Rainfall in the Sahel would tend to follow that. Warmer Atlantic would tend to mean more precipitation in the Sahel. El Nino events, we expect more El Ninos with a warmer Pacific, with a cooler Pacific, fewer El Ninos, and global air temperatures as well tend to increase during El Ninos and decrease during more La Nina periods. And so all of these are evidence of strong and weak phases of the so-called conveyor belt. Well, I looked at that and it made a lot of sense. In fact, this is what I was looking at in 1994. This is 100 years of precipitation from the Oregon coast. It's pretty much representative of the Pacific Northwest. And what you see is 4 more or less distinct periods of mostly cool and wet years and mostly warm and dry years. Now, these are anomalies or departures from average. So one of the things that I noticed right away is here's the zero value, an average year, and there aren't very many average years. Mostly we get wetter years, positive anomalies, wet years, or dry years, or the red. So all you need to do is remember, blue is wet, red is dry. Now, over 100 years or so, there's about an equal number of reds and blues, but there are also periods of about 25 years or so where there is a predominance of one color or another. Notice, for example, from about 1920 to 1945, it was mostly reds. That was a very warm period, as you'll see momentarily. And we know now, we didn't know it at the time, but we know now that this was a period dominated by El Nino events in the Pacific. And warm and dry is the El Nino signature in the Northwest. Something changed in the late 40s. We went into about an almost 30-year period of mostly blues. About 3 out of 4 years in the warm dry period were red, and about 3 out of 4 in that period were blue. And then we were in 20 years, at the end of 20 years of mostly warm and dry years, again dominated by El Ninos. The blue period was dominated by La Ninas in the Pacific. And back at the beginning, we see the tail end of a La Nina-dominated cool wet period. So in 100 years, 4 more or less distinct periods. Now, it's not always easy to draw the lines on exactly when they happen. The one exception is right here. In 1976, there was a dramatic change that just happened in a single year. But there's some arbitrariness that needs to be shown, but nonetheless, there's evidence of these periods of 20 to 25 years, roughly a 50-year cycle in weather and climate in the Northwest. So I took Bill's little plot and I added something to it. The fourth line down, Pacific Northwest precipitation, really matched up with those periods. The strong conveyor belt, which is representative of warm Atlantic, cool Pacific, more La Niñas, tends to be wet, and they tend to be cool, dry, wet, dry, and so on. And then there's global temperature anomalies down at the bottom. So Bill's theory really appealed to me a great deal. Let's talk about the ENSO connection, the El Nino Southern Oscillation. A lot has been written, it's been studied a lot. And there are the three phases, the kind of average or normal in the middle, the La Nina at the top, the El Nino at the bottom, sea surface temperatures with the cool tongue here during an average year, a much bigger cool tongue in a La Nina, and with an El Nino, the cool tongue more or less disappears. Ocean temperatures are more or less uniform. And I think you can see the landmarks, South America, Central America, the equator. This window that we're looking at is the most significant source of terrestrial heat to the atmosphere, the so-called warm pool. There is more heat that comes out of that window than any place else, and therefore, major changes or disruptions or redistributions of the sea surface temperature in this zone affect not only the Pacific Basin, not only the northern hemisphere, they literally affect the entire world. Generally, the closer you are to this, the more they affect you. So the Pacific Northwest is closer than the east coast of the U.S., and the effect is stronger, but as you'll see, the effects are very, very widespread. And this shows at least some of there's the teleconnections. Teleconnections are the effects of changes in the El Nino Southern Oscillation and how they're manifest in different parts of the world. So there's a cartoon of at least some of the teleconnections. And then there's the salmon connection. Now, salmon is considered one of the bellwether species in the Pacific Northwest, an indicator. Some people call it one of the canaries in the coal mine. And there's been some concern about dwindling numbers of salmon, and along with it, the suspicion that it's people that are really influencing salmon populations. This is a chart that was produced by Jim Anderson of the University of Washington for a testimony in the House of Representatives in, I believe, 1993. This shows a 5-year running average spring Chinook salmon in the Columbia River. And the fish counts began in 1938, and this is through about 1990 or 91. And what you see are, I don't know if you can see these numbers. They're pretty small, but anyway, big numbers mean more fish, and this means less fish. So from the 50s, 60s, early 70s, there were large numbers of salmon that returned, and then it just kind of fell through the roof in the mid-70s and stayed low. Anecdotal information from this period suggested that the 20s, 30s, and early 40s were rather poor from the standpoint of fish returns, but the early part of the century was actually pretty good. So it does certainly suggest that there was something cyclical that was going on. But the big concern was this one, that something caused the fish to basically be gone. There were many fewer fish, averaging here about 180,000 a year, down here to maybe 60 or 70,000. Now this was a chart that Jim Anderson prepared, and he and a fellow named Kurt Ebbesmeyer came up with an index. They call it the Pacific Northwest Index, and you notice the blue here matches the blue, and the blue is relatively cool and wet periods. The red is warm and dry. And the red periods pretty much coincided with the periods that we either measured fewer fish returns or at least anecdotally assumed that. So this was something that really suggested a correlation between what's going on in the local climate and ocean conditions and salmon. Now in 1994, when we looked at spring Chinook, this is my chart, 5-year average. That's what we were looking at. And the talk around the Northwest was the fish are going away, and it's because of either overfishing or habitat or dams or those darn foresters cutting down all the trees. I mean, it had to be one of those four. And there was tremendous concern about this, but those of us who were looking at a little bit different picture had different ideas. In the mid-90s, several things happened, one of which was that based on Bill Gray's predictions of a return to an active Atlantic, basically, I didn't say this, but in 1993, Bill predicted that we were almost at the end of that cycle and we were going to turn back into a much more active Atlantic hurricane period. In other words, he felt that that conveyor belt thing was going to reverse itself. And the more I looked, the more I decided that he was probably right. And so in 1995, 2 years after Bill, I stuck my neck out and said, in the Northwest, we are going to go from a mostly dry period that we've had 10 dry years in a row, to a mostly wet period. In 1996, this cycle that you kind of see developing here was first named by the University of Washington. They were looking at this simultaneous with me, and I should have named it. I could have called it whatever I wanted, I guess, but they named it the PDO, the Pacific Decadal Oscillation. And then in 96, I predicted that the salmon returns were going to increase as well, because I felt that the most significant influence on salmon was the combination of climate and ocean conditions. Now here's the PDO. The upper left chart shows the areas that are that basically flip-flop in terms of temperature. The eastern tropical Pacific and the mid-latitude North Pacific. And then this is the Pdo Time Series. So it looks an awful lot like the chart that I showed you of Oregon precipitation, with a period from about 1920 to 1945 of mostly red, associated with El Nino events. The period from the mid-40s to the mid-70s, mostly blue, associated primarily with La Niñas. And then that 20-year period from 1976 to about 1995, again, mostly red, and then kind of ups and downs since then. Here are some of the characteristics of the PDO as it shifts back and forth from one mode to another. The Aleutian low pressure center shifts westward or eastward depending on which phase. By the way, the positive phase is the mostly El Nino phase, and the negative phase is mostly La Nina. Storminess, precipitation, density on the and the rivers and the estuary currents change. We see these flip-flops in a lot of different physical parameters, and in addition, some of the natural resource parameters like fish and birds and so on. At the top is a time series of the, time series of the strength of the Aleutian low. When we have an El Nino event, you tend to get a deeper Aleutian low, which forms a ridge over the west coast. The La Niñas tend to have less tendency towards an Aleutian low and a stronger mid-latitude jet, and the jet stream tends to be over the northwest. Now, sometimes this PDO changes really quickly, and the most dramatic one, it's one that was mentioned by Pat Michaels last night, is the one in 1976. In a one-year period, there was a dramatic change in a whole bunch of ways. And one of the ways it was manifest was this step change in temperatures in Alaska. This is from the Alaska Climate Research Unit, and this is an average of temperature at 4 cities in Alaska, Nome, Barrow, Fairbanks, and Anchorage. And basically you have very little change prior to 1975 and very little change after, and about a 2.5 degree Fahrenheit step change between 1976 and 1977. So a tremendous change in the PDO that manifests itself in a big change in Alaskan temperatures and changes really throughout the Northwest. Here's another parameter that we really pay attention to in the Northwest. It's an Upwelling Index. It's developed by a fellow named Andrew Bakken, and it's based primarily on the surface Ekman transport caused by winds. When winds are strong and blow from north to south, you tend to get Coriolis, essentially pushing or diverting the surface water offshore, allowing upwelling to occur. And upwelling is really essential for productivity of the ocean. The more the upwelling, the more the small creatures can feed and multiply, and the more food there is for the bigger fish. So the periods with higher upwelling tend to be more productive. And what you can see from this is something, again, looks rather cyclical, with a peak in the 60s and early 70s, a trough in the 80s, and then rising again in the late 90s to about this time. I plotted the PDO, the annual PDO, with the Bakken Index, and it generally matches up pretty well. And especially in the last 35 years or so, the PDO tends to lead the Upwelling Index. So that's a pretty good indication that we do have a cause and effect. Obviously, the Bakken Index isn't going to affect the PDO, but it makes sense that the PDO would affect that because of the big change in weather patterns. So as we go back and we look at that 5-year average in salmon, summer Chinook returns, and now bring it up to date, this is what we see. As we apparently have had a PDO shift in the mid-90s, we've seen a tremendous turn back upwards in summer Chinook, and matching really quite well what we see from the PDO. Other researchers, this is Chavez et al., writing in Science in 2003, and you probably can't see these letters either, but the PDO is right here with the negative values, the La Nina values, the El Nino values here, and they've compared it with a bunch of other parameters. I can't see what the top one is because it's cut off, but there's an atmospheric circulation index, Mauna Loa CO2 changes, a regime indicator series for anchovies and sardines, and an ecosystem index. And they have a cartoon that describes those phases, the so-called cool phase and the warm phase, more conducive to anchovies and sardines, and some evidence of the beginning of a regime shift in the early 90s and a full-blown regime shift in the late 90s. Here's another paper from GRL by Bill Peterson with the PDO at the top, the zooplankton numbers in the second number, the coho survival, and northern copepods at the bottom. Again, a lot of evidence is piling up that these multi-decadal cycles are affecting a variety of climate and natural resource parameters. And so here's the water year precipitation brought up to date since the shift in the mid-90s. Now, during this period, we've had 2 very dry years. We've also had 7 that were quite a bit wetter than average and 4 that were pretty close to average. So it pretty much matches the 75-25 kind of ratio that we've seen in the past. I'm still perplexed about those 2 really dry years, but this year we can add another wet one to the mix. Now, one of the other ways that this is manifest is in long-term temperature trends in Oregon. And of course, this is something I pay a lot of attention to. If we look at the long-term stations in Oregon, these are all HCN stations, unadjusted data for HCN stations. We see a pretty similar pattern. This is Bend, 1902 through 2005, and what we tend to see is that peak in the 30s, early 40s primarily. The peak in temperatures is mean annual temperature, with a warmish year in 1934, and then cooler, and then warming up slowly, but still the warmest temperatures in Oregon occurred in the 30s and early 40s. Here's Condon, which is in north central Oregon. Same deal. Again, evidence of not a steady rise in temperature, but rather the cyclical effect with the warmest period in the 30s. Pilot Rock, a little farther east, same thing. Corvallis, where I live, same thing. We see that peak in the 30s and early 40s, a decline, and then a rise thereafter. Now, there are stations that are heavily influenced by urban effects that show unprecedented temperatures recently, but rural stations, high-quality rural stations, really show this kind of a distribution throughout the state. And in fact, if you compare Corvallis temperatures with PDO numbers, you get a very good matchup. That warm, dry period in the 20s, 30s, early 40s was a period with rather significant temperature increase. The blue Pdo period in the 50s, 60s, early 70s was much cooler, and then we've seen some rise lately. But again, we're not seeing unprecedented temperatures in Corvallis or anywhere in Oregon. We see the same thing in the Arctic. Some seminal work by Igor Polyakov and co-authors, and you've probably seen this. This is Arctic temperatures from 1970 to now, and with a quote you hear a lot, Arctic temperatures have increased, and they have. But what's wrong with this picture?
It doesn't start in 1940.
It doesn't. Yeah, and the x-axis goes all the way back to 1880. Well, you know what Paul Harvey would say? He would say, I'm going to tell you the rest of the story, and of course there's the rest of the story, which reminds me of temperatures in Corvallis and in Pilot Rock and in Bend, and reminds me of the PDO. Now, I don't know if that caused that, but whatever, there's so much correlation between those two that I have to say if that one didn't cause that, then whatever caused that also caused that. So where does it all start? Does it start with solar? Does it start with the ocean? Probably starts with solar, but that's one of the research topics that I think we'll continue to delve into. And if we look at U.S. temperatures, this is from NCDC, we see the same thing. We see this warm, dry PDO was existing concurrently with what was arguably the warmest time we've seen. Now, this doesn't really show that, but you do see this cyclical kind of a distribution with the peaks corresponding to positive PDOs and the troughs responding to negative PDO periods. And then there are the glaciers. You may have heard about Glacier Park. Glacier Park is another one of these places that's talked about a lot. This is a picture from 1910. And when people study glaciers, one of the parameters that they look at is where, elevation-wise, the bottom of the glacier is, the terminus. And that's one of the primary ways that they measure the size and the extent of a glacier. How low was that? Generally, the colder it is, the lower it is. You had glaciers in Little Ice Age that were down into the towns, and without a doubt, the glaciers have receded in Glacier Park. This is from a paper by Greg Peterson, Dan Faggre, Steve Gray, and Lisa Gromlich in 2004 in GRL that I consider to be really, really significant. Here's photographs, 1910, 1997. Clearly, the glaciers have receded since 1910, without a doubt. But let's look behind that a little bit. They're charts from two of the biggest glaciers in Glacier Park. Now, these take a little while to figure out. I'm used to time series, and I've been showing nothing but time series, but this is more like a distance series, where they show the distance from the trim line versus the elevation, and then they plot times on there. It's not really obvious to me what that meant, so I went back and I replotted it as a time series. I took their data points and I replotted them as a time series. So here's what you get. The Jackson Glacier, 1840 to present. What you see from beginning in their record in the 1850s was a little bit of melt until about 1920, and then a whole lot of melt until about 1940, and then a little bit of melt after that. So yes, the glacier has receded a great deal, but most of the recession occurred during that very warm, dry decade in the 20s and 30s. Some paleoclimate people in the Northwest have suggested that period, and it's based on tree rings, which aren't perfect, that period was the driest period in the Northwest in the last 500 years, at least. And that combination of warm and dry is a killer when it comes to glaciers. Now here's the other one, which I think is even more dramatic, the Agassiz Glacier, which hardly died back at all until 1920, and then about 90% of the dieback, or the ablation, as the glaciologists say, occurred in between 1920 and 1940. So when you see the rest of the story, you realize that most of the melt occurred prior to the real buildup of greenhouse gases. Now this is a chart from their paper, and the red period showed times when ablation was likely. That means it was dying back. And then accumulation was likely during the blue periods. One of the things they pointed out was that at 1850, And that's really when people started paying attention to Glacier Park, and about when cameras were invented. That was probably the most extreme glacial advance of the Little Ice Age. And a lot of people consider that to be the end of the Little Ice Age. So they felt that the glaciers were at their maximum at that point when we started paying attention to them. And then there were some ups and downs until about 1920, and then you see that big rapid retreat, as they call it, the big red splotch that lasted for about 25 years. And then since then, you've had some ups and downs. What they've done since 1900 is they've superimposed the values of the Pdo on there in the black dotted line. And you can see how nicely the Pdo matches up with their periods of ablation and accumulation. Here's what they concluded from that study. The Pdo and the local May 1st snow water equivalent are negatively correlated with an R of, should be minus, I think, 0.76. An R squared, that gives you an R squared of about 0.5. And they said we can then use the reconstructed values of the Pdo as a proxy for winter accumulation potential for the Jackson and Agassiz glaciers. In other words, Pdo is really what seems to be the most significant independent variable in glacier growth or glacier ablation in Glacier Park. Now, from all of these disparate kinds of data, temperature, precipitation, glaciers, salmon, other species, I haven't shown the snowfall, but if you're interested, I could show you that. From all those things, what I conclude is what really causes climate change, at least in the Northwest, probably around the Pacific Rim, maybe in many other parts of the world, is this combination of Pdo and ENSO, probably with help from the sun. And the sun may very well be the most significant influence that influences Pdo and ENSO, and then other things besides. So I'm going to stop there. I'd be glad to entertain questions. And if you're interested in the snowfall story, I can show that too.